This is a presentation of the Transmission Electron Microscope Fundamentals, which was Lab 5 of Class MSc 421 at Arizona State University for the spring semester 2016. In the group are Dylan Hiscok, Joseph Leslie, Damien Gonzales, and Gary Phelps. A quick look at the history of microscopes. The early Romans around 100 AD were the first known users of lenses. They were mainly used to magnify the sun's rays to start fires and had a magnification of about 4 to 6. The 13th century, we saw early simple microscopes that were really only magnifying glasses that had one power, usually around 6 to 10 times. Dutchman Anthony Leeuwenhoek has since been called the father of microscopy, and he found that by grinding and polishing he was able to make small lenses with great curvatures, and these rounder lenses produced greater magnification than ever before, and his microscopes were able to magnify up to 270 times. Little was done between his time and the mid-19th century to improve the microscope. German Ernst Abbe originally proposed that the ability to resolve detail in an object was limited approximately by the wavelength of the light used in imaging, which limits the resolution of an optical microscope to a few hundred nanometers. Abbe was the first to define the term numerical aperture as the sine of a half angle multiplied by the refraction index of the medium filling the space between the cover glass and the front lens. And in 1873 he published a formula that is still used today: D equals lambda over the quantity 2n times sine alpha. The picture to the right was taken from a display in the Physical Science Building B Wing at Arizona State University. The Y scale is measured in angstroms. The need for greater resolution drove the research. After all, if visible light can only get you down to a couple hundred nanometer resolution, what could possibly get you down to see greater detail? And it was found that the de Broglie wavelength of electrons was many orders of magnitude smaller than that for light, which theoretically allowed you to image at atomic scales. And through much research in the early 20th century, the first transmission electron microscope was invented in 1933 by Max Knoll and Ernst Ruska at the Technical College in Berlin, Germany. These two pictures were also taken at the same display at the Physical Science Building B Wing, Arizona State University, and is a side-by-side rough comparison of the construction of a light and the TEM microscope. You can see how similar they are, as they all have roughly the same construction. The image to the right is a picture taken from a light microscope that we had used during a previous lab. Generally, for light microscope images, the object is 5 micrometers or thicker, and the image is formed due to the absorption of light waves. The image can be seen directly and is usually in color. The resultant power is 250 nanometers, and you can have magnification up to 4,000 times. And light microscope images today are used to study details of gross internal structures. The image to the right is an actual image taken from the display screen of the TEM we were using for this lab. For TEM images, the object is ultra thin. It's usually 0.1 micrometers or less in thickness, and the image is formed due to the scattering of electrons. The image can only be seen on a fluorescent screen and is always in black and white. For TEM, the resolving power is between 0.5 to 5 angstroms, and magnification can be up to 300,000 times. And the kind of information you can get from a TEM image is topographical, morphological, compositional, and crystalline. You can actually see the lattice structures on TEM images. For the TEM design, there are 5 main sections of components. At the top, we have the electron source, which is often called the electron gun. Next comes the condenser lenses, which concentrates the electrons. After that, we have the sample stage, which, as the name implies, holds the sample. Following that, we have the magnification section, and it's just a series of lenses that is used to magnify the image. Then at the bottom, there's a data collection system, and it uses either a fluorescent screen or a CCD screen. There is also a vacuum vacuum system associated with the TEM. And the reason we need a vacuum is because we're using electrons as our source, and they can be easily deflected if there are stray atoms inside the chamber. The TEM source uses a beam of electrons instead of visible light. This is because the wavelength of the electron is much smaller than that of visible light, and this allows us to have much better resolution. The electron source emits electrons from a cathode, of which there are two types, accelerates them by high voltage, then uses an electrode to stabilize the electron beam, and an anode to apply the acceleration voltage. And there are two main types of sources, thermionic emissions and field emissions. In the thermionic electron gun, the electrons are emitted from a heated filament, then accelerated towards an anode. There are two types of filaments used, the tungsten filament, which requires a temperature of 2800 Kelvin, and the LAB6 crystal, lanthanum hexaboride, which requires a temperature of only 1800 Kelvin. The LAB6 crystal is much more robust and has a longer life than the tungsten, and is becoming the filament of choice in the electron gun. The thermionic electron gun is very similar to how a light bulb works also. A bias voltage creates a repulsive electrostatic field that condenses the cloud of primary electrons produced by the filament. The Wilmot cylinder is an electrode in the electron gun assembly used for focusing and to control the electron beam. Down near where the beam narrows before it expands again, you'll find D/O, which is known as the crossover, and this is the effective source of illumination. The anode at the bottom is a positive charge, and its function is to accelerate the electron beam. The second source, and the one used in this lab on our TEM experiment, is the field emission gun. It uses a very strong electric field to extract electrons from a metal tip. The metal tip is a single tungsten crystal wire etched to a needle point. Strong curvatures produce high field strength with low voltages, and it gives a much brighter source brightness. The temperatures are lower than the thermionic, but it requires a much stronger vacuum. A grid provides an electric field that extracts via a tunneling mechanism. The anode is a positive charge plate that accelerates the beam, and the crossover point there at the end is the source of illumination. The size of the source is important in high resolution. This is a picture of the tungsten tip of the field emission gun. In case the scale at the bottom of the picture is not clear, it's measured at 200 micrometers, so you can see just how small it really is. In optical systems, light waves are bent in lenses by changes in the refractive index. However, in electron microscopes, electron waves are bent by magnetic fields from current traveling in coils of wire. The electrons close to the center are less strongly deflected than those passing the lens far from the axis. This has the overall effect that a beam of parallel electrons is focused into a spot, the so-called crossover. The focusing effect of a magnetic lens therefore increases with the magnetic field, and the magnitude of the field is controlled by the amount of current that goes through the wires. The image comes out of the other side of the electromagnetic lens inverted and rotated depending on the magnification through the lens. The image on the left shows a cross-section of what an electromagnetic lens looks like that is used in the TEM. You can see in the center of the pole, which is surrounded by the wire coil, and this is what generates the electromagnetic field. On the outside of the wire coil are the cooling pipes, and it is covered by a thermal distributor so it doesn't overheat. The pictures on the right were actually taken here in the lab. The one on the picture on the left shows a whole electromagnetic lens, and the one on the right obviously is showing a cross section of what one looks like.
One of the most difficult parts of using a transmission electron microscope is creating the sample. This is because the sample needs to be thin enough for the electrons to pass through it. There are several steps in preparing a sample. As you can see, steps 1 through 4 involve cutting the sample into a small enough size to begin working on it. Step 5 thins the sample, and step 6 makes the sample into a bowl shape, which will be very thin in the center. For step 7, the sample is mounted onto a washer so that it can be handled without breaking, And finally, the sample is ion milled to about 100 nanometers thick, where it will be transparent for electrons. The goal of all of these steps is to get the sample as thin as possible. This diagram shows the tools used to shape the sample, as well as the shape of the sample after they have been processed by the tool. First, the sample will be ground down until it is about 1/10 of a millimeter thick. Next, the sample is dimpled, and the center of the sample will be approximately 5 micrometers thick. Finally, the sample can be placed into the ion mill, where it will be ground down from the opposite side until the center is approximately 100 nanometers thick. In order to cut the sample, a high-speed saw is used. The saw blade is coated with diamond dust, which will allow it to precisely cut through the sample. After the sample is cut, it will be approximately 2 millimeters along its length and width, and approximately 1/2 of a millimeter thick. Because the sample is so small, it is mounted onto a wax cylinder in order to be easier to manage. This is done by heating the wax on a hot plate and placing the sample on top of the wax so that it adheres to it. Next, the sample will be ground down to make it thinner. The wax cylinder with the sample attached to it will be placed into a holding device, which will ensure that the sample remains level while it is ground down. Next, the sample will be placed onto the polisher, where it will be ground down by either a very fine sandpaper or a polishing cloth in a very fine abrasive solution. After this step, the sample should be less than 1/10 of a millimeter or 100 micrometers. Now that the sample is very thin, it is ready to be dimpled. In order to do this, the sample, which is still mounted on the wax cylinder, is placed into the dimpling machine. As you can see, the copper-colored wheel is spinning, grinding away at the material, while the base rotates, so the sample is given a bowl shape instead of a slot. After this step, the sample will be approximately 5 micrometers at its thinnest point. Next, the sample will be mounted onto a washer so that it can be safely handled. This is done using vacuum tweezers, as the sample is too small to easily be worked with by hand. Because the washer is a standard size, it also allows the sample to be mounted inside the transmission electron microscope. The final step in processing the sample is to ion mill it. This sample is placed into the ion milling machine, and argon atoms are fired at it, which will knock material off the surface. Now the ion milling is done on the opposite side as the dimpling, and will be thinned until it is approximately 100 nanometers thick at its thinnest point. Now after all of these steps are completed, which will usually be about 8 to 10 hours of work, the sample is finished and ready to be placed into a transmission electron microscope to be observed.
The TEM's upper limit of resolution and magnification allows for imaging of atomic columns. It's possible to determine defect location and type and sample from this capability. Good chemical resolution and crystal structure data can be taken directly from the diffracted electron beam or from auxiliary equipment attached to the TEM. By the nature of how this device works, it also has a very large depth of field. There are a few different limitations on TEM machines. The samples must be stable under a high vacuum. Aberrations limit the resolutions near angstrom distances. And it is difficult and destructive sample prep, which causes a lot of problems when beginning to use the machine, and the operation of the machine also requires extensive training.
Resolution. Resolution is the measure of sharpness of an image. It is equal to the wavelength divided by the numerical aperture of the lens. The numerical aperture distinguishes the range of angles that the system can accept or emit light. The TEM is able to image at a drastically higher resolution than light microscopes because of the small de Broglie wavelength of electrons. The resolution of the TEM is approximately 2 angstroms. Aberration-corrected TEMs, which computer controls the currents of the lenses, have a resolution of 1 angstrom. The resolution can produce images of single columns of electrons. At smaller magnifications, the contrast in the image is because of the absorption of electrons in the material, due to the thickness and composition of the material. And at higher magnifications, complex wave interactions adjust the intensity of the image. With a transmission electron microscope, you can perform the following: view sections of material, get electron diffraction patterns, view fine powders suspended on a thin film, make a 3D image by tilting a sample and putting together the images, analyze the composition and some bonding differences, perform electron energy loss spectroscopy of the beam passing through a sample to figure out the sample composition or the bonding states of atoms in the sample, view small whole organisms such as viruses or bacteria, physically manipulate samples while viewing them, such as indent or compress them to measure mechanical properties, view frozen material, and make X-ray or characteristic X-rays from samples from microanalysis. Identify the pertinent features of these two cartridge brass specimens. Due to the appearance of defects in this sample, as noted by the red arrows, it is the 60% cold work cartridge brass. This sample has no visible defects. This leads to believe that this sample has been annealed at 800 degrees Celsius for 1 hour.